Okay, so now we're going to put our predictions into a variable called predictAttend in our Dodger train data frame. So let's first check our Dodger train data frame, see if we actually have that. So we do have that. And we're going to add a new variable called predictAttendance. And that is going to have, remember this is our model, and we're going to apply the predict function to our model. So our model contains all kinds of stuff. We saw, we did the str on this, and we saw it's a big list. But if you, the predict function will take certain parts of that out of the model, and make predictions on with the given model that we have, which we saw was here. So this is actually, I should have attendance equals all this. So attendance is the output variable, and then it's a function of all these input variables. Okay, so that's the idea. If you have questions about that, let me know. But that's the idea. So this prediction function is going to use that model with the input data, and it's going to make a prediction. So let's try that and see what we get. Okay, and so if we just print it out, we should get so these are the predicted values. Okay, now they're not the same as the actual values, right? Predicted is not the same as the actual. Now here I'm getting some help on predict, and it's over here. Now I don't see anything talking about an argument called new data, because he uses an argument called new data, and I don't see any mention of it, but it could be mentioned in here, because these are sort of other versions. It might be in here, but I don't see it there either. Here, new data. Okay, so these are kind of the versions that are called by the predict, depending on what you're doing. It will, so the predict is the general form, but specifically when we're doing a prediction on a linear model, it calls the predictLM function, and that has a new data argument, an optional data frame in which to look for variables with which to predict. If omitted, the fitted values are used. Now I did a search for the fitted value, and that's the values for an output variable that have been predicted by a model. So I think what that means is that you you start with your original data set, and you make predictions with those values. But we are starting with not our original data set, but we are, so we're not using our training data set, we're using this data set. Okay, so I guess that's the idea here. So anyway, we're going to do that, and that will be on our training set. I'm sorry, on a testing set. Okay, so I'll go back to here. Okay, and then we have like that. Okay, so now we'd like to measure how well the model did. So we want to compare these values, which are predicted with only from within our test set, but still our test set has the true values, and these are our predicted values. So we like to look at the difference between the actual values and our predicted values, and that gives us some idea of how well we did, or in other words, how well the model performed. So he does that by looking at the correlation between the actual attendance and the predicted attendance. Okay, and we get a correlation of this. So means that not super high, but it means that we could say that our model accounts for, he says, the proportion of the test set variance accounted for. So in other words, how much did our model account for the values, or actually the changes in the values. But anyway, so we can say that it wasn't bad. It was our model is doing some work for us, but it's definitely not capturing the entire variation in attendance. We'd like to capture the entire variation. That would mean we're predicting exactly correctly the attendance, but we aren't doing that, not with this model. Okay, so now he merges the training set and the testing set using R-bind, which means we're combining rows. We're not adding columns together, we're adding rows. So first we're going to have all the rows of the training set, and following that we're going to have all the rows of the testing set. So let's do that. So that's our so-called plotting frame. So that's all of our data, testing and training, but it also has our predictions in it, right? It still has our predictions in it, because these had our, I think it had, did that have our predictions or not? Yeah, this had our predictions in it, and I guess the other one also had predictions in it. And next he's going to look at do some visualization of everything that we've done. So he says to show to management. So you want to show your results to your manager. So you're going to do this visualization. We're going to use this XY plot, which I think was in the lattice. So let's see, I won't go through all this. Let's just see what it looks like. So we get that. So how can we analyze this? So we have two graphs here. We have a graph for the training set and a graph for the testing set. We have bobblehead games and no bobblehead games. We have across here the actual attendance versus the predicted attendance. So we'd like everything to be on this straight line. That would mean that the predicted was exactly the same as the actual. That would mean we were doing a perfect job. But anyway, what can we say about this? So one thing we could say is that I think the model seems to be, these dots seem to be closer to this line than these dots do to this, maybe. If that's true, I'm not sure if that's actually true, but if that's true, then we would say that the model works better on the training set than it does on the testing set, which is basically, we would expect that, right? Because the model was built on the training set, so we would expect it to work better there. But what we really care about is how well it works on the testing set, where it wasn't built. Because that's the same as like how it would work on unrelated data. By unrelated, I mean data that wasn't in the training set. And you can check the text in the library to see if he gives any further discussion of what kinds of conclusions we can draw by looking at this, and how you could explain to management how well your model is working. Okay, and finally, the last thing we want to do is, or the last thing he's going to do is use the full set of data to obtain an estimate of the increase in attendance due to bobbleheads. So you want to know how important, how much do bobbleheads increase in attendance. So he's going to apply the model to the whole Dodgers data set, and then he's going to call that this, and he's going to print it. So let's try that. And here, among other things, we have the coefficients, and this tells you how important each coefficient is, like, or rather how significant each coefficient is. And then that is basically, this tells you that the t-value, so for those of you who have studied statistics, which I hope is all of you, you should know this. Anyway, so the bobblehead, oh, that's the p-value. Okay, so the estimate for the coefficient is here. Okay, the estimate for all the coefficients. So this one is, so this tells us that by using a bobblehead, we expect, all other things being equal, to increase attendance by 10,000, which is pretty significant, it sounds to me, since the whole stadium only holds 56,000. That's a pretty significant change. And the next thing he does is he tests the significance of the bobblehead promotion. So basically that means, okay, we just found that it was 10,000, but how much can we believe that number? I mean, is it, that's our best estimate, but is it, are we confident about that estimate, or are we not confident about the estimate? So that's another statistical concept that hopefully you've seen in the past, but that we want to know how confident we can be in the fact that we said that it was 10,000. And so we get this here. Okay, so that's all we're going to do for this chapter. So we've explored the linear model, and we have talked about training and test sets, an important part of data mining. Linear models are really not necessarily part of data mining. They're part of statistics and also part of data mining. But training and testing is usually not done in statistics, but it is done in data mining. Now you might say, well, why not? Well, maybe because statistics is an older study, and there wasn't that much data available, so it wasn't necessarily so easy to separate a data set into training and testing. So they didn't really do that very. I never saw that done in normal statistics, but it always seems to be done in data mining or data science. Okay, so anyway, we learned about that. We did learn about the linear model, and we're also, I think we'll have a chance to study some other kinds of models in R. Of course, we also do that in our data mining class at APU, and also we're going to study ARIMA, which is a kind of time series modeling process. Okay, so we'll stop here.